So I think you guys won't have problems securing employment by the end of April.
Hey, Elena.
Yes, Kelly.
Hey, did you say we would have our quiz marks today?
Yes.
Okay, thanks.
Yeah, I'll upload them at the end of class, and then you guys can review your quizzes. Those who got 6, you won't have anything to review. I just didn't want to upload them yesterday because I knew you guys had a test, and so I just typically try not to upload marks on the day that you have a test. And I wasn't sure what time your test ended. Okay, I'm going to start to record. I don't forget. Okay, well, good morning and welcome to week 6 of Geotechnical Materials 2. I guess we're almost halfway through the course, so that's exciting for you guys. So today, the agenda for today is we're going to talk about settlement and compressibility, and then we're going to keep on along the same topic or the same lines of information, but we're going to discuss time to consolidation. So how long does it take for a specific layer of clay to consolidate? So settlement and compressibility, you can calculate settlement for different soil types using different equations. So if you want to calculate settlement using sort of cohesionless material, so a sand and gravel material, you'll use either the elastic settlement equation, or you can use your SBT value, so your N value, to calculate settlement. If you want to calculate settlement in clay material, we have different equations depending on if the material is considered over-consolidated or normally consolidated, or if the clay material is considered drained or undrained. So we're going to have discussions on how you determine which equation you use and then how you go through the calculation process. So that's the agenda for today. I anticipate it will take us about 2.5 hours to make it through the material. So I'll give a brief overview of theory, and then we'll work through a bunch of example problems today. I think we have about 6 or so that we're going to work through today. So I'm going to share my screen, and like usual, if you have any questions as I'm discussing the theory, don't hesitate to ask. Okay. I'm assuming you guys can see my screen. Perfect. Okay. The first slide is just sort of an overview of what we'll be discussing today. So we've already gone through that. The next slide discusses elastic settlement and what is the elastic settlement, or sorry, the elastic modulus and Poisson's ratio that you use for the different equation types. Sorry, it's an in-service day. So elastic calculations, so your elastic settlement calculations only apply to cohesionless material. So it only applies to a sand material or a silt material that has no clay, or a gravel material. So that's your elastic settlement equation. And then also for your SBT equation, so if you have an N value, you can use that N value to calculate settlement as well, but that, again, that also only applies for sand material or gravel material. We have different equations that we use for material that has cohesion, so a clay material or a silty clay material. And the elastic modulus that we use in that equation has to be the drained modulus. And we can only determine our drained elastic modulus from doing consolidation tests, or from doing a consolidated drain triaxial test, or a drain direct shear test. So what I want you to take away from this sort of complicated slide is elastic settlement equations are used for cohesionless material. So a sand material or a gravel material or a cohesionless silt. And then we have different equations that we use for material that has cohesion, so a clay material or a silty clay material. And you'll have to know if the material is consolidated or normally consolidated or over consolidated when you do the calculations. Elastic settlement equation is shown in this slide here. So in this equation, SE represents your elastic settlement. So when you're doing your calculation and you go through and you do it, your settlement would be in meters. You can convert that settlement from meters to millimeters. However you choose to report it, it's marked correct. Generally, we report settlement in millimeters. But if you prefer to report it in meters, that's okay. Q represents your pressure on your foundation or the stress that's being applied to your foundation area. So Q has units of kPa. B represents the smallest dimension of your foundation. So similarly to what we talked about yesterday, if you had a 2 meter by 4 meter foundation, rectangular foundation, B would represent the 2 meter dimension. It's the smallest dimension of your foundation. E is your drained elastic modulus. In a cohesionless material, your drained and undrained modulus are basically identical, and that's because you don't generate any excess pore water pressure when you add a load or you apply additional pressure to a foundation material that doesn't have cohesion, and that's because you have almost instantaneous drainage or dissipation of that excess pore water pressure. Mu there represents your Poisson's ratio, and your Poisson's ratio is dimensionless, whereas your elastic modulus has units of kPa. CS is a factor, and the CS factor is taken from a table or from a formula, and your CS factor depends on various factors. One would be your foundation shape. So if your foundation is rectangular or square or circular, that impacts your CS value. If your foundation is rigid or flexible, that also impacts your CS value. That being said, most of our foundations that we design, we consider them to be flexible foundations. I talked to one of my friends who primarily designs foundations in southern Manitoba. That's primarily what his roles and responsibilities are. And he's only ever designed one rigid foundation in his career in the last 20 years. So we primarily design flexible foundations. It also depends on the thickness of your soil layer beneath the foundation area, and also whether you're calculating the settlement at the center or at the edge of your foundation. So I'm going to pause there. Does anyone have any questions on the elastic settlement equation? No, okay. This just shows you a rigid versus a flexible foundation. So the schematic on the left represents a rigid foundation. And with a rigid foundation, your settlement is equal everywhere. So for example, in a rigid foundation, you wouldn't have more settlement at the center of the foundation compared to the edges. Your settlement is equally distributed and your settlement is equal across the entire width of the foundation. That being said, you do have a greater stress distribution at the edges or the corners of your foundation compared to the center of your foundation. If you look at the schematic on the right, it represents a flexible foundation. And with a flexible foundation, your settlement varies across the width of the foundation. So with a flexible foundation, you have the greatest settlement at the center of the foundation and the smallest amount. Okay, and so the smallest amount of settlement is at the corners or the edges of the foundation. So that's the difference between a rigid and a flexible foundation. We have a building code. So we have a national building code and a Canadian Foundation Engineering Manual. The maximum amount of settlement that you're allowed to have with a structure before it exceeds the national building code is 25 millimeters or 1 inch. So that's the maximum amount of settlement you can have for a structure before you've exceeded the building code. 19 millimeters is the greatest amount of differential settlement you're allowed to have without exceeding the guidelines in the building code. And differential settlement represents the difference in settlement between the center of your foundation and the edge or the corner of your foundation. If you were building an embankment structure and that embankment structure was going to have greater than 25 millimeters of settlement, there isn't an issue with that because the embankment structure doesn't represent a physical structure or a building where you could have cracking in the drywall or cracking of a concrete or a structural foundation. I think I talked about last week how we built a ring dike in St. Adolphe, and when we did our calculations, we anticipated there would be about 6 inches of settlement or 150 mils of settlement over about a 250-year time period. This is just an example of the various shapes, our foundation shapes, and what B represents or is associated with the different foundation shapes. So with your rectangular footing, B represents the smallest dimension, and with a circular footing, B represents the diameter of the foundation area. Okay, I'm going to pause there. Does anyone have any questions before I move on to the tables? No, okay. This is the first table that I'm going to show you. This table was developed by McCarthy. So this is a table that you can use to determine what your factor is or what your CS value is for your elastic settlement equation. This table applies for both flexible and rigid foundations. So you'll see here, this table right here is the table you would use if you had a rigid foundation, whereas if you had a flexible foundation, this is the table that you would use here. So this is the table if you have a flexible foundation. With a flexible and a rigid foundation, you will have to know what the ratio, your L to B ratio is. So that simply represents the ratio of the longest dimension of your footing to the smallest dimension of your footing. So if I had a rectangular footing that was 5 meters by 10 meters, my L to B ratio would be 2. So for example, if I wanted to determine what my factor would be, if I wanted to calculate settlement at the center of my foundation, my factor that I would use would be 1.53 for a flexible footing. If I had a rigid footing, my same factor would be 1.12. And you can just use these tables to determine the value. These tables should be provided on the equation sheet for the course material. These aren't values you're expected to memorize. You just obtain them from the table. The one catch with these two tables that are provided is there is an assumption that the thickness of the soil layer beneath the foundation area is greater than 10 times B for these values to apply. So say, for example, I had a foundation width of 2 meters. Well, then to use these charts, I would have to have a thickness of soil layer, or my thickness of my soil layer would be at least 20 meters beneath my foundation area. So that is the one catch for using these tables. Any questions on how you would use this table here to determine your factor for either a rigid or flexible footing? Yes, you would just simply do a linear interpolation if you had an L over B of 3. Correct.
If we're worried about settlement, couldn't we just do more compaction or something like that?
It gets difficult in your foundation area to go in. You would have to over excavate all the material, and then you would have to place it in lifts of 150 mils and then compact it. So in the Red River Valley, you can have clay material that ranges between 15 and 33 meters. So it's not realistic to go in and you know, you can't excavate down 33 meters and start to compact. So if it's a smaller clay layer, Tim, yes, you would go in and you would over excavate, and then you would place your material in 6-inch lifts and compact the material. Yep. We usually reserve that for anything. 2 meters is getting on the high side. Like if you had a clay layer or another type of soft material that was less than 1 meter, you would typically go in and over excavate. Okay, here is another table that you can use to determine what your CS value is. This is a table that was produced by DAS. There are limitations with this table as well. This table here only applies to under the corner of flexible rectangular footing. So if we look at this here, this table only applies to under the corner of a flexible rectangular footing. With this table here, you have to know your L over B ratio. So similarly to the previous table, you would have to calculate your L over B value. And you also have to determine what your H over B value is. So H represents the thickness of the layer beneath the foundation. So say if you had a 5-meter thick sand layer, H would represent that 5 meters. And if the dimensions of your foundation were 5 meters by 10 meters, B would be represented by the number 5. So your H over B ratio would be 1. Tim, I guess further to that point with, wouldn't you just remove the material and compact it better? Elastic settlement associated with sand is generally not going to exceed the National Building Code guidelines. So generally your settlement associated with sand is less than 25 mils, or your elastic settlement associated with sand is less than 25 mils. So you don't usually have those issues where the building code requirements can't be achieved. With clay, most definitely. That's the reason why all structures in Winnipeg have to be piled instead of using a shallow foundation. With the exception of residential structures, you can still use a shallow foundation. And that's because we can never have, it's very difficult for us to achieve less than 25 mils of settlement with structures that are being constructed in the Red River Valley. So yes, this applies to a flexible rectangular footing. You have to know your H over B ratio and your L over B ratio. And then you would use the same methodology as we discussed yesterday to determine what your settlement would be under the center of a flexible footing. So you would divide your footing, your rectangular or square footing, into 4 equally sized smaller rectangles, and then multiply your elastic settlement value by 4. And I'll work through an example problem with this.
Elena?
Yes.
If you were to experience elastic settlement around the foundation of your home, what would that exactly mean?
It would just be, you would notice that there might be a little bit of cracking in your walls. Your doors might not close properly. Like we always joke with our house that our house must have been built in April, because that's the month of the year where our doors close the best. So you would just probably notice a little bit of cracking.
Okay, would it feel like almost spongy?
Like, is there just certain times of year you feel the sponge?
It's like right now.
Okay, that's probably not related to elastic settlement, because elastic settlement occurs almost instantaneously, right? So it would be when you immediately load a structure. So that's when your elastic settlement occurs. Right now, it's probably just doing, it's probably more related to the thawing of the soil, like around your foundation area.
Okay, thanks.
Yeah. Has anyone ever noticed their neighbors watering their foundations in the summer? That's one trick that some people do. Just what to prevent it's more the drying process, you know, the wetting and drying process. When it's really dry in the summer, some people water around their foundation to prevent cracking of their foundation.
I would do that on my old house. Otherwise it would, yeah. It was a 3/4 basement and it was on piles, but it would kind of be exposed when it was really dry and mice would come in.
Oh, yeah. Yeah, we do it as well. Like in the summer, I water my flowers and then I water around the foundation of my house. And then I'm just doing that to try to prevent cracking of my foundation. Oh, yeah. Well, the newer houses, even though they're piled, they would still have the same issue. So that's a slight digression. But yeah. Okay, so DAS does indicate that settlement of a rigid footing is 93% of the value that settlement would be for a flexible footing at its center. So a rigid footing would have slightly less settlement at the center than a flexible footing would. These are representative or typical values of the elastic modulus and Poisson's ratio for different material types. I don't expect you to memorize these. This is just a reference table for you when you're working out in industry. One thing to note is you'll notice, especially with material that has cohesion, so a soft clay, for example, has a lower elastic modulus value than a stiff clay does. Whereas its Poisson's ratio is higher for a soft clay than it is for a stiff clay. These are just representative values, and again, I don't expect you to memorize them. You'll always be provided your elastic modulus and your Poisson's ratio value on a test. So you won't have to use this table to determine what the value is. I would give that value to you on a test. Okay, let's take a pause there. I'm going to work through a couple example problems associated with elastic settlement. Does anyone have any questions before we start the example problems? Okay. Stop sharing my screen. Okay, can you guys see this here? Yeah, perfect. Okay. Okay, we're going to go over example problem 7.1. So this is an elastic settlement problem. The problem doesn't specify that it's in sand material or a cohesionless material, but we'll just imply that it is. So you have a rigid concrete footing. It's 4 meters by 2 meters, and it carries a total load of 2,500 kilonewtons. So it's asking, what is the elastic settlement if the elastic modulus is 12,500 kPa and your Poisson's ratio is 0.3. So this is the equation that we use to calculate elastic settlement. So your elastic settlement is equal to your factor times your pressure, so your Q value, times the the smallest dimension of your footing divided by your elastic modulus times 1 minus your Poisson's ratio squared. So you'll notice in this problem here, your Q value wasn't provided, but your load in kilonewtons was provided. So we know that we can convert our load in kilonewtons to a pressure by using Q is equal to P divided by A. So we know P is 2,500 kilonewtons, and we know the area of our foundation is 4 meters by 2 meters. So if we go 2,500 kilonewtons divided by 8, the pressure that's being applied to the foundation area is 312.5 kPa. The next component that we need to determine is our factor value. So we know that this is a rigid footing because the problem identified that it was a rigid footing. So we know that we can only use the table that's provided by McCarthy at this point, or I guess we can, yeah, so that's the only table that we're able to use. So we know that we need to know what our L over B value is. So we know that the longest dimension of our footing is 4 meters, and the smallest dimension of our footing, or our B value, is 2. So we know our L over B value is 4 divided by 2, which is equal to 2. So we'll go and we'll use this table by McCarthy because this is the only table that we can use for a rigid rectangular footing. We'll see here, if I have a rigid foundation, I have an L over B value of 2. Therefore, I know my CS value is 1.12. So that is my factor value that I would use in my elastic settlement equation. So I take that value and I'd input it into my equation. So I know for a rigid footing with an L over B value of 2, my CS, or my factor value, is 1.12. So to calculate my settlement, my CS value is 1.12. My Q value is 312.5 kPa. I use millimeters. You can use either millimeters or meters in the equation. It doesn't matter. I just said that the smallest dimension of my footing was 2,000 millimeters. You could also just use 2 meters. Divided by 12,500 kPa, because that's my elastic modulus, times 1 minus 0.3 squared, and 0.3 is my Poisson's ratio. So I calculated my elastic settlement in this situation to be 51 millimeters. Anyone have any, or if you wanted to represent it as meters, you could go 0.051 meters. Anyone have any questions regarding the process for this problem? No? Okay. I know some of you have worked through this material. Again, if you have any questions when you're working through the material, don't hesitate to ask. Yeah, that one was the easy one. So now I'm going to go work through the hardest one. So this is example problem 7.3, or it'll be 11.3 in your notes. A 3 meter by 6 meter flexible rectangular footing overlies a 6 meter thick compressible soil having an elastic modulus of 4,000 kPa and a Poisson's ratio of 0.4. The applied load is 1,200 kilonewtons. So there's two components to the question. The first one is asking what is the settlement under the corner of the footing and what is the settlement under the center of the footing. So we're going to start with what is the settlement under the corner of the footing. So if we look at this problem here, our foundation is 3 meters by 6 meters. And we know that because we're calculating the settlement under the corner of the footing, that we can use the McCarthy table, because we know that in this instance here, the thickness of our soil layer isn't greater than 10 times B. So since our soil layer is only 6 meters thick, it's not greater than 10 times B, which would be 30 meters in this instance. So we'll use the McCarthy table. And we also have a flexible foundation, so it's possible to use the table. So in this instance here, when we use the McCarthy table, we have to know what our L over B value is, and we also have to know what our H over B value is. So L over B in this instance is 6 meters divided by 3, which is 2, And H over B is represented by also 6 meters over 3. It's just a coincidence that they're both the same value, that the length and the thickness of the soil layer are the same. So both our L over B and our H over B values are 2. So we could use this table here if we know H over B is 2 and we know L over B is 2. We know that our factor value or our CS value is 0.29 because that's where our two lines intersect. So again, I'm drawing similarly to what I demonstrated yesterday. I'm drawing a horizontal line from our H over B value, and where that intersects with the vertical line from L over B, that's our CS value. So our CS value in this instance is 0.29. The next part, again, we weren't provided with our average stress or our stress value. So we have to determine what our stress is from converting our load into a stress. So we know that Q is equal to P over A. We know our P value was 1200 kilonewtons. That was provided in the problem. And we know the area of our footing is 3 meters by 6 meters. So we were able to determine our Q value, which is 66.7 kPa. So now it's just plug and chug into the formula. We know our factor value is 0.29. We know the stress applied to the footing is 66.7. We know the smallest dimension of the footing is 3 meters. We know our Poisson's ratio is 0.4, and our elastic modulus is 4,000 kPa. So once you plug and chug through, you can calculate your elastic settlement to be 12 millimeters or 0.012 meters, or it would be 12 millimeters. So this is a similar process to the process from example problem 7.1. Anyone have any questions on the process for this part of the question? Yes, correct. You can work in either meters or millimeters as long as you're consistent. You'll notice the kPa values. So the kPa from your stress and your elastic modulus cross out on both the numerator and denominator, so they cancel each other out. So the only dimension left is either your meters or millimeters from your B value. So you can use either McCarthy or DAS. It depends on the information that's provided in the question, Saraz. So here you are given information on the thickness of your soil layer. If you have no information on the thickness of your soil layer, you can use McCarthy. Oh, sorry. We use DAS in this instance here. So McCarthy applies to the table where the smallest dimension of your footing, the thickness of the soil layer has to be greater than 10 times B. So that doesn't apply in this instance. So sorry, yes, we use DAS in this equation or in this problem here. So if I said McCarthy, I was incorrect. I meant to say we did use DAS in this instance. So use McCarthy when you don't have any information on the thickness of your soil layer. If you have information on the thickness of your soil layer, make sure you use the DAS table. Okay, so next let's go through with doing the calculation for the settlement at the center of our foundation area. So again, we're going to use the DAS table where we have to determine what our L over B value is and our H over B value. So if you remember back to the slide, I said the process for calculating the settlement at the center of the footing using the elastic settlement equation is similar to the process that we use for external loads, where we had to divide our rectangular foundation area into 4 equally sized rectangles. So you'll see here, our initial foundation was 3 meters by 6 meters. So now I've divided my footing area into 4 equally sized rectangular footings that are now 3 meters by 1.5 meters. So to go through, we use those smaller dimensions of the footing to go through and determine what our CS value is. So in this instance here, L over B, L represents the longest dimension of our footing, so that is 3 meters. And B is the smallest dimension of our footing. So the smallest dimension of our smaller rectangles is 1.5 meters. So our L over B value is still 2. H over B does change in value. So H is still 6 meters. So the thickness of our soil layer beneath the base of the foundation is still 6 meters. But B, the smallest dimension of our smaller rectangles, has changed and is now 1.5 meters. So our H over B value is 4. So we'll look at our DAS table here. And you'll notice here, we don't have an H over B value of 4. We have an H over B value of 2 and an H over B value of 5. We still have our L over B value of 2. So I would go down and then I would note, okay, I don't have a 4, I have a 2 and I have a 5. So I would simply just do linear interpolation between the value of 2 and 5 on the table here. So if my H over B value was 2, my CS value would be 0.29. If my H over B value was 5, my CS value would be 0.52. So I would simply just do a linear interpolation between the two. I've shown the process here on how you would do the linear interpolation, so take some time to review that. But by doing the linear interpolation, you do get a CS value of 0.44 for an H over B value of 4. That being said, if I was to give you a question like this on the test, I'm not going to be asking you to do any interpolation. This is just sort of the hardest problem that I could ask you. So again, yeah, I'll check that equation after, Pavel. So then I would go through and similarly, it would be sort of the plug and chug. So I know my factor or my CS value is 0.44. Q is still 66.7 kPa. Q doesn't change by 4 because it doesn't matter, Fabian, and I'll show you this because if I went Q divided by 4, it would be 300 kilonewtons divided by the smaller dimension of my footing, so 3 meters by 1.5 meters. So I could go through and do that, Fabian, and my Q value still works out to be 66.7 kPa. So I probably should have shown it that way, like the 300 kilonewtons divided by the 3 meter times 1.5, but it still works out to 66.7 kPa. So Q is 66.7 kPa. B, the smallest dimension of our footing, is 1.5 meters. Our Poisson's ratio is 0.4, and our elastic modulus is 4,000 kPa. The one thing you'll notice that I did here is I multiplied everything by 4. And that's because I want to determine the total settlement at the center of the footing. And if I didn't multiply my answer by 4, I'm only calculating what the settlement would be at the corner of one of these smaller footings. But because I want to know what the settlement is at this corner, for this rectangle, this corner here, for this rectangle, this corner here, and this corner here, so I know what the total settlement is at the center of the footing, I've multiplied my settlement value by 4. So that's why I've used a 4 in the equation. And so the total settlement at the center of my footing is 37 mils or 0.037 meters. The one thing that should be a takeaway from these problems are if you're to calculate the settlement at the center and the corner of a structure and you have a higher settlement value at the corner compared to the center, double check your calculations because that should never be the case. you should always be calculating a higher settlement at the center of the foundation than you should be for the corner. Anyone have any questions on this process? They're the same, Say-Wan. So if you're calculating the center of the settlement at the corner or under the corner, it means the same thing. Yesterday, sorry, I forgot to record the session. I apologize profusely. I have made videos, though, of the example problems that I went over yesterday in the class. So there are videos posted on Learn of me working through the example problems. And I'm happy to meet with students if they have questions on the example problems that I have the videos of. I need these sessions to record automatically when I start them. Sometimes you have so much going on, you forget to press record. Do you guys, okay, I'm going to go over a few more slides and then I think I'll give you guys a break, say for 10 minutes, and then we'll come back and then we're going to work through conducting settlement calculation questions. I want to give you guys a break before we get into the next section because it's really important and I need you to fully comprehend it. Unless you guys want to keep going, you can tell me otherwise. Measuring elastic modulus, we don't measure our Poisson's ratio. That's very rarely measured. Elastic modulus, you can measure your undrained elastic modulus from a UCS test or potentially from a CU test. Your drained elastic modulus, which is a really important value to use if you want to calculate your elastic settlement, can only be determined from a consolidation test or a CD triaxial test. Again, we're not going to spend much time on that. So I just wanted you to be aware of that. This just sort of shows you the methodology in how you could calculate your elastic modulus from a consolidation test. Again, just based on how the course is being delivered, I don't think it warrants a lot of time spending on this. Just be aware you can calculate your elastic modulus from a consolidation test. Okay, how are you guys feeling? The next concept is uber important, and I really need you to be wide awake and ready to learn it. Do you guys want a 10-minute break before we get into it? Okay. So let's come back at 9:55. And then we're going to get into how you determine if a soil is normally consolidated or over-consolidated and the various equations you use depending on the stress state of your soil. So go get some coffee. You're going to have to be wide awake for this. This is one of the biggest takeaways from this unit. And the test next week will be really hard if you don't have an understanding of this. So get some caffeine and we'll meet back at 10:55, or sorry, 9:55. Sorry, Pavel. You can just use the data points that are provided to you to calculate your CR, so you don't have to graph it necessarily. Okay, hopefully everybody is back. Okay, my screen should be shared. Are you guys okay with me just sort of lecturing and then going through example problems? Like, did you guys want to be more interactive where I put you in groups and you work through example problems yourself, or what works for you guys? Okay, well, up to you guys. I'm always open to suggestions. Okay, if you have to pay attention to anything this whole class, this is where you should be putting or concentrating your efforts. This graph here is similar to the graph that we discussed last week. This represents a consolidation curve, a void ratio versus your log effective vertical stress. From this consolidation curve, you're able to calculate three parameters: your compression index, or your CC value, your recompression index, or your CR value, and also your pre-consolidation pressure. Obviously, you were tested on this on your lab quiz, and if you were unsure what you were doing on the lab quiz, make sure you become comfortable with it for the test next week. Okay, so now we're going to move on to discussing how do you calculate settlement for a material that has cohesion. So either a clay material or a silty clay material. For those of you who have reviewed the material, you'll notice that there's three different equations that were presented, and you have to have an appreciation or an understanding of the situation before the external load is applied and after the external load is applied to determine which equation is appropriate for the scenario that's being presented. So there's three different scenarios. So the first scenario is calculating consolidation settlement for a normally consolidated soil. So we discussed last week that a normally consolidated soil is a soil that is at its largest stress or largest pressure that it's ever experienced. So it hasn't experienced a higher pressure or stress in the past. So a normally consolidated material is one that is represented by where its overburden pressure or its existing stress state is equal to or greater than its pre-consolidation pressure. So say, for example, you calculated your overburden stress to be 120 kPa. And you knew your pre-consolidation pressure was 120 kPa, or say 115 kPa. So you know that your overburden stress or your initial effective stress is greater than your pre-consolidation pressure. And so it lies to the right of your pre-consolidation pressure on your on your void ratio versus log effective stress graph. So if that is the case, where your initial effective stress is greater than your pre-consolidation pressure, your soil is considered normally consolidated. And if your initial effective stress is greater than your pre-consolidation stress, then just inherently, your final effective stress is also going to be greater than your pre-consolidation pressure. So if that is the case, your soil is initially normally consolidated, and in its final stress state, it's also normally consolidated. So you would use this equation here that's provided on the slide. So you would use this equation here to calculate your settlement associated with that external load being applied. So you would use this equation where you have your compression index, so your CC value. You would know the thickness, so H naught of your clay layer of interest. You would know your void ratio. You would know what your final effective stress value is because you've calculated it, and you would know what your initial effective stress value is because you've calculated that as well. So CC, H naught, and E naught are always provided to you in the question, and you would be expected to calculate your final effective stress and your initial effective stress. And then from that, you could calculate what your settlement would be for that clay layer. So that's the first scenario where your soil is considered normally consolidated and it will always be normally consolidated, even after you've applied an external load. The next scenario is sort of a scenario where your clay layer is considered over-consolidated. So an over-consolidated material, as we discussed last week, is its current stress state is less than a stress state that it has experienced in the past. So we talked about examples where there was glacial loading of the overburdened material in southern Manitoba. So the stress state of the lacustrine material in southern Manitoba was at one time greater than what its current stress state is. You can have anthropogenic influences such as heavy equipment. Maybe you have artificial lowering or raising of a groundwater table. So there are other factors that come into play. Other reasons why your soil may have experienced a higher stress state in the past. Maybe you were doing some preloading to accelerate the consolidation, that sort of thing. So an over-consolidated soil is where both its initial and final stresses are less than your pre-consolidation pressure. So those two values would lie to the left of your pre-consolidation pressure on a consolidation curve. So say, for example, I had a consolidation or a so I had a pre-consolidation pressure of 120 kPa. I had an initial effective stress of 80 kPa, and I had a final effective stress of 100 kPa. So both my initial and my final effective stress are less than my pre-consolidation pressure. So therefore, I know my soil was initially over-consolidated, and in its final stress state, it was also over-consolidated. If this is the case, you would use the formula that's provided on this slide here, where again, H naught and E naught would be given to you in the question. Your recompression index CR would also be given to you in the question. There will be poor water pressure, Pavel, and I'll work through example problems with that, but total stress is not assumed to be effective stress. So effective stress is always effective stress where you have to take poor water pressure into account. So yeah, your CR, your recompression index would be given to you in the problem, and then you would be calculating your final effective stress and your initial effective stress, and then going through and doing the plug and chug to calculate what your settlement would be for this scenario. That being said, settlement for a normally consolidated material is always much, much larger than it is for an over-consolidated material. And that's because your CC and your CR values are very different. Your CC value is the value of the slope of the line of the steep portion of your consolidation curve. So your CC value is always much greater than your CR value. Therefore, the settlement associated with the normally consolidated material is always much greater than over-consolidated material. Again, remember the example, we come back to Brandon, where we had that normally consolidated material along the floodplain of the Assiniboine at the 18th Street Bridge, and we were going to get 1.1 meters of settlement. That's a large amount of settlement compared, say, to the clay in the Red River Valley down in St. Adolphe, we were going to get 6 inches or 150 mils of settlement. Still a large amount of settlement, but not in the range of what we were expecting to experience and which we did see in Brandon. Any questions on, I have one more scenario to go through, but I'll pause here because the next scenario is a little more complicated. Any questions on how you determine if a material is normally consolidated or over consolidated? Yep. So let's go back to normally consolidated. So normally consolidated material would be material where your initial effective stress and your final effective stress are both greater than your pre-consolidation pressure. So say, for example, you had a pre-consolidation pressure of 120 kPa, but your initial effective stress was 130 kPa, and your final effective stress was 150 kPa. That would be a normally consolidated material, and that's because your initial and final effective stress values are larger than or greater than your pre-consolidation pressure. Does that help? Okay. Okay. So the final scenario that you could be presented with is what I will call the hybrid option. So the hybrid option is a scenario where your initial effective stress is less than your pre-consolidation pressure. So it lies to the left of your pre-consolidation pressure on your consolidation curve. But your final effective stress is greater than your pre-consolidation pressure. So we'll go back to our pre-consolidation pressure of 120 kPa. So if our initial effective stress was 100 kPa, that's less than our pre-consolidation pressure of 120 kPa. So initially, the material is over-consolidated. But if we calculate our final effective stress to be 140 kPa, our final effective stress is greater than or larger than our pre-consolidation pressure of 120 kPa. So it lies to the right of our pre-consolidation pressure on our consolidation curve, and it's greater than. So then our final effective stress is in the normally consolidated state. So this is sort of a hybrid option where initially the soil would be considered over-consolidated, but in its final stress state, after you've applied that load, it's in its normally consolidated state. If that is the case, we have this whammy of an equation to use, and it's this equation right here. So delta H is equal to H naught, which is just the thickness of your soil layer, divided by 1 plus E naught. And then that's times by your recompression index times the log of your pre-consolidation pressure divided by your initial effective stress, plus your recompression index times the log of your final effective stress divided by your pre-consolidation pressure. So you can go through, and that's all in brackets again. You can go through and plug and chug through those numbers, and you would be able to calculate what your settlement would be for the hybrid option. So the hybrid option, the settlement typically lies between what settlement you would calculate for a normally consolidated material and an over-consolidated material. How was that for an explanation? Did that make sense?
Kind of.
Kind of. What was confusing? I'm happy to go back. Do you think it would help to work through an example problem where we could apply it?
Well, to be honest, it's kind of hard for me to really get the content by listening to someone teach it. I kind of have to go in there and spend 3 hours fighting with it to actually understand it. But that's just me, so don't read into that much.
Okay. Well, it might be the entire class. The CR value, you will always be given the CR value in the question, but we typically use the CR value from the lower portion of the consolidation curve. Yep, we're going to do 2 examples actually. And slide number 20 here, it just provides an overview of the 3 consolidation equations that you would use to do your calculations. So this just summarizes the equation for normally consolidated material. For the hybrid option, where your material is initially over-consolidated and then becomes normally consolidated, and then the option or the scenario where your material would always be over-consolidated.
Question. So these three cases, they only apply to soils with cohesion, right?
Correct. Exactly, Tim. These equations only apply to material with cohesion. So you would only use these equations for a clay material. You would use your elastic settlement equation for material that doesn't have cohesion. These equations here actually calculate your elastic settlement and your consolidation settlement for your clay material. We assume that it's calculating both of them together. So that's an assumption we make. Okay, I'm going to work through example problems 7.6 and 7.8 with you guys. Sharing my screen. No, you don't need to state any assumptions on the exam. What is this doing? So that would be why. Okay, example problem 7.6. This example problem here is asking you to calculate or determine the settlement below a 6 meter by 3 meter footing due to consolidation of the clay layer. The problem states that there's an increase in stress due to the 2,600 kilonewton load at the center of the clay layer, which is at 4 meters in depth, and that increase in stress is 70 kPa. So this problem here gives you some parameters of the soil. So it provides the specific gravity, and it provides the dry density of the soil. Also provides a moisture content, so you can go through and determine what your unit weights are for the various soil layers. So you would have a different unit weight for the sand material above the groundwater table, a different unit weight for the sand below the groundwater table. So above the groundwater table, your sand would be gamma bulk, and below the groundwater table, your sand would be gamma sat sand. And then in this problem here, the clay layer would also be saturated because it's below the groundwater table. So you would calculate the unit weight of the clay layer as well. So this is very similar to what we did in Unit 4. So we in Unit 4, Module 4, we went through and we determined how to calculate the unit weights for the various stratigraphies. So I'm not going to spend a lot of time on how we went through and did the calculations for the unit weights. For the sand above the groundwater table, we know what our P dry value is. We knew what our moisture content was. It was 5%. So knowing our moisture content and our P dry value, we were able to go through and calculate what our bulk unit weight was. So the bulk unit weight of the sand was 17.3 kilonewtons per meter cubed. Hopefully that's a little bit better. To calculate the saturated unit weight of the sand material, To calculate the saturated unit weight of the sand, we first of all had to calculate the void ratio. And then once we knew the void ratio, we could calculate our saturated density, which we could then convert to a unit weight. So I've gone through that process here, and you can follow through with those calculations after. But the saturated unit weight of the sand material was calculated to be 20.1 kilonewtons per meter cubed. The same process was followed for the clay layer. We were provided a specific gravity and a drive density of the clay material. So we had to go through and calculate our void ratio for our clay material. And once we knew the void ratio, we could calculate our saturated density and convert that to a unit weight. One thing to note when you're doing calculations, the void ratio of a sand material is sort of in the 0.5 to 0.65 sort of range. So when you're calculating your void ratio for sand, if you're up around 1, double check your calculations. There's something that's not right. Or if you're above 1 for sand, like you've calculated 1.5 or something like that, you probably forgot to subtract 1. So you should be looking for something in the 0.5 to 0.6 ballpark for sand. And clay typically varies between 0.9 and or 0.8 and 1.1. So again, with clay, if you're in the 2s or if you're down and at 0.5, double check your calculations because there's something that's probably not right. So if we take a look at this stratigraphy here, you'll note that our sand layer is 3 meters thick and our groundwater table is located 1 meter below the ground surface. And then you'll notice in the problem here, our clay layer starts at 3 meters below the ground surface and continues until 5 meters below the ground surface. So in this example problem here, we know that the thickness of the clay layer is 2 meters. So one important thing to note is when you're calculating the settlement for a clay layer, we always calculate the settlement in the center of the clay layer. And the reason for us doing that is if we calculate the settlement at the center of the clay layer, it represents an average settlement value for the entire clay layer. If we were to calculate the settlement at the top of the clay layer, well, that doesn't represent the clay layer because it's at the top and there's still 2 meters of clay beneath it. And if we were to calculate settlement at the base of the clay layer, well, that will over-represent the amount of settlement that would have occurred in the upper region. So we always calculate the settlement at the center of the clay layer, just as an average value that would represent the entire thickness of the clay layer. So in this instance here, we would be calculating the settlement in the middle of the clay layer, which is 1 meter below the sand layer, or 4 meters below the ground surface. Does anyone have any questions on that? About why we would do that?
Yeah, as opposed to doing that for sand, like that wouldn't make any sense for sand, right?
Yeah, sand is instantaneous, so you don't take it in the center for sand. Sand, you just consider the entire thickness of the sand layer. With clay, you do consider the entire thickness of the clay layer when you use your settlement equation. But yeah, it's different for sand.
So is this like a question that'll be on the test where we have to provide all our work?
What I have done, Kelly, on the test is guaranteed you'll have a settlement question. I have broken the settlement question down into about 5 different questions. So I've led you really step by step through the process, and you'll have a question associated with each of those 5 different steps. But say, for example, you made a mistake on part A. It doesn't depend on you getting part A correct to get part B correct. Because in part B, I will say, assume this value and move forward. So no, you don't have to hand in your work because I've laid it out step by step. And nothing is worth more than, I think, 2 marks when you're going through the step-by-step process.
Okay, thanks.
Yeah. There will be one question in which you hand in your work for, and I'll send an email out. It will be a graphing question in which you will hand in your work for. But guaranteed, there will be a settlement question on your test. I just couldn't make 36 original settlement questions or 36 different scenarios. So that's why I did it like that. Okay, so to calculate your initial effective stress, we're always calculating yes, someone did do the research, not me. I'm not that theoretical. So when we're calculating our initial and final stresses, we also calculate our initial and final stresses at the center of the clay layer as well. So if we look at our stratigraphy here, we have 1 meter of sand above the groundwater table, 2 meters of sand below the groundwater table, and then there's a 1 meter distance from the base of the sand layer to the center of our clay layer. So if I want to calculate my initial effective stress, so my initial effective stress is my overburden stress of the soil stratigraphy before I've added that external load or before I've added that additional load. So this is the process. So my initial effective stress is always sigma V naught prime. So sigma V represents vertical stress, this naught represents initial, and prime represents effective. So my initial effective stress is 1 meter thick sand layer above the groundwater table times the bulk unit weight of sand, which is 17.3, plus, so this is gamma bulk sand, plus 2 meters of sand material below the groundwater table times my saturated unit weight of the sand, which is 20.1, minus the unit weight of water, which is 9.81, plus my 1 meter thick clay layer from the base of the sand layer to the center of the clay layer, times my saturated unit weight of the clay, which is 18.4, minus 9.81, which represents the unit weight of water. So my initial effective stress is equal to 46.5 kPa. So that would be my initial effective stress. So what I recommend, and you can find a way that works best for you, but sometimes making a little table sort of simplifies things. So I made a little table here where I have my initial effective stress, and then I have these words NC or OC. So what I'm trying to determine from here is my initial effective stress normally consolidated or over consolidated? And then I have this delta sigma V, which is my increase in stress due to the external load. So let's work through this right here. So we know that our initial effective stress is 46.5 kPa. What is our pre-consolidation pressure of the clay material? What was it identified to be? It was 100 kPa, right? So is my initial effective stress normally consolidated material, or does it represent an over-consolidated material? Right. And why does it represent an over-consolidated material? Someone else? Right. Because my initial effective stress is less than my pre-consolidation pressure, which is 100 kPa. So that's why my initial effective stress would be considered over-consolidated. So the problem here states that my increase in stress due to my vertical load is 70 kPa. So my delta sigma V was given in the problem. I didn't have to calculate it. So it's 70 kPa. So now I'm going to determine what my final effective stress is. So my final effective stress is always my initial effective stress, so my sigma V naught prime, plus my increase in vertical load. So the problem here told me it was 70 kPa. So my final effective stress is adding 46.5 plus 70 kPa. So my final effective stress is 116.5 kPa. So now I need to determine if my final effective stress is in a normally consolidated state or in an over-consolidated state. So what do you guys think? Correct. And why is it in a normally consolidated state? Correct. Correct. It's greater than 100 kPa, which is our pre-consolidation stress or pressure. So therefore, my final my final state is normally consolidated after I've added the external load. So therefore, this gives me a clue. My little table gives me a clue to which equation I should use. So based on the information here, which equation am I using? Tessa, 70 was given in the problem. You didn't have to do a calculation. Right, the hybrid, so the big equation. So I know, based on the information in my little table, that I need to use my hybrid equation. So I've written the hybrid equation out here. And also the hybrid, all the equations are provided between example problem, I think, 7.6 and 7.7. So here I know that my thickness, so H naught represents the total thickness of my clay layer. It doesn't represent the thickness of my clay layer to the center. It represents the total thickness of my clay layer because I'm trying to calculate the settlement for the entire clay layer. So H naught is 2 meters because my clay layer is 2 meters thick. I know my E naught value is 0.942, and I know that because I calculated it for my clay layer. Generally, I would give you what E naught is in the question. CR was given in the problem, and CC was given in the problem as well. Or did they forget to give CR? Well, CR, we're just assuming is 0.09. And CC is 0.25. So if we look at here, so our CR is 0.09. We know our pre-consolidation pressure is 100 kPa, and we know our initial effective stress is 46.5. So we know that these are the parameters that we use in the equation here. And then we would add our CC value, which we know is 0.25, times the log of our initial, yes, CR was just missing, but it would always be given, Jonah, times the log of our final effective stress divided by our pre-consolidation pressure. So we know our final effective stress is 116.5 kPa because we calculated it, and we know our pre-consolidation pressure is 100 kPa. So we would go through and just plug and chug through the numbers, and we could determine that our settlement is 48 millimeters or 0.048 meters. I'm going to pause and give you guys a few moments to look at this. Okay, yes, Fabian. So in real life, you would go through and you would calculate the elastic settlement for your sand layer. So there would be problems, for example, where I might say calculate the consolidation of the clay layer, and then the next step would be calculate total settlement, where if I asked you to calculate total settlement, it would be consolidation of the clay layer plus the elastic settlement of the sand layer. But if I just ask for consolidation of the clay layer, you only have to go through this process here. Okay, anyone have any questions on how we did the consolidation calculation for the clay layer? Okay, perfect. Fair game on the test. I'll be very explicit if I ask you to calculate consolidation of the clay layer, or if I ask you to calculate total settlement. I think I've broken it out on the test, truthfully, where I get you to calculate elastic independent of consolidation. But I can't remember 100% because I wrote the test in September. And then I'll go over example problem 7, 8. And then after we go over example problem 7, 8, we'll take a break. Can you get a sample test to practice? I have a review assignment online, which would be, I won't say it's identical to the test that you will be given, but if you can do the review assignment, you'll be able to most definitely do the test that will be next week. Same with the example problems. If you have a good comprehension or a good understanding of the process for the example problems, then the test will be no problem. The test is easier than the example problems. Okay, here's another example problem. This is example problem 7, 8. This problem is asking you to use the influence coefficients to find the stress at the center of the clay layer, and then under the corner and under the center of the footing. I'm just going to concentrate on under the center right now. It asks you to compute the settlement due to the elastic compression of the sand and consolidation of the clay. So Fabian, this is where you would be calculating what the total settlement is. It says you can assume the sand layer is infinitely thick. That way you could use the McCarthy table for the elastic settlement. What is the potential differential settlement between the center and the corner of the foundation? And I'll just sort of show you the process of how you would determine that. So again, the unit weights for the different material wasn't provided. You were more provided material properties, and from those material properties, you could calculate the given unit weight. So you'll see for this example problem here, your groundwater table is located at 1.5 meters below the ground surface. So you know from this information that there's a 1.5 meter thick sand layer that would be considered unsaturated, or there's a sand layer where you need to calculate the bulk unit weight. Then you know your sand layer beneath the groundwater table is saturated, and also your clay layer beneath the groundwater table is saturated. So you have two unit weights to calculate. Your saturated unit weight of the clay material was given, but you still need to calculate the saturated unit weight of the sand and the bulk unit weight of the sand. So in this question here, you weren't provided with your dry density. You have to calculate what your dry density is. But you'll notice in this problem here, you also weren't given your void ratio, but you were given your porosity. So you know from your phase relationships that you can calculate your void ratio if you know your porosity. So I went through and calculated my void ratio. And once I determined my void ratio, I was able to calculate my P dry value. And once I knew my P dry value, I was able to calculate my bulk density. And from my bulk density, I could calculate my bulk unit weight. I'm not going to spend time going through this process because you guys are probably very comfortable with these equations. So I calculated my bulk unit weight of sand to be 19.1 kilonewtons per meter cubed. So I also need to calculate what my saturated density of my sand material is. So my saturated density, you're very comfortable with the equation. We've used this quite a bit in this course. So I was able to work my way through and calculate my saturated density of my sand material. And then from my saturated density of my sand material, I was able to calculate my saturated unit weight. So my saturated unit weight of my sand is 21.1 kilonewtons per meter cubed, and the bulk unit weight of my sand is 19.1 kilonewtons per meter cubed. So the first step in my problem is to calculate my initial effective stress. So where am I going to calculate my initial effective stress to in this problem if I'm going to calculate the consolidation settlement of my clay layer? At what depth below the ground surface, or where in the clay layer? Right, so you're going to calculate it at 4 meters below the ground surface, or 1 meter into that saturated clay layer. Exactly. So to calculate my initial effective stress, I know I have 1.5 meters of unsaturated sand, and I'm going to multiply that by the bulk unit weight of my sand material. So I know the bulk unit weight of my sand is 19.1 kilonewtons per meter cubed. And I'm going to add that to, I know I have 1.5 meters, so from here to here, of saturated sand material. So that's 1.5 meters of saturated sand material times the saturated unit weight of my sand minus the unit weight of water. And then I will also add, because I'm calculating my effective stress in the center of that clay layer, and the center of the clay layer is 1 meter beneath the base of the sand layer. So I have 1 meter of clay times my saturated unit weight of clay, which is 18.9, minus the unit weight of water. So I know that my initial effective stress is 54.64 kPa, or 54.6 kPa. Anyone have any questions how I calculated that initial effective stress? Because we are calculating what the average settlement would be. So when we're calculating what the average settlement would be, we take the center of the clay layer. If we took it at the base of the clay layer, we would overestimate what the settlement would be for the clay layer, because it would be an overestimation. If we took it at the top of the clay layer, it would be an underestimation. So we take it in the center, so it's a sort of a representative average of the entire clay layer. Okay, so now let's move on to using our influence coefficients. I'm going to use the influence coefficients to determine what our increase in vertical stress would be at the center of the clay layer. So if we remember from our influence coefficients from yesterday, I have to calculate both what my M value is and my N value is, so I can use the chart. And again, when I'm calculating it at the center of the foundation area, I need to divide my foundation into 4 equally sized rectangles, so that I know my initial foundation was 4 meters by 8 meters. But if I'm going to divide that into 4 equally sized rectangles, I'm now going to have a 2 meter by 4 meter rectangle. So the 4 meters represents my L value because it's the longest dimension of my rectangle. So my N is 1/2 times L divided by Z. I know that I'm trying to calculate the increase in vertical stress at the center of this clay layer. And I know the center of this clay layer is at a depth of 4 meters below the ground surface. So I know my Z value is 4, and I know 1/2 times L is also 4. So I know my N value is equal to 1. Same thing with M. M is 1/2 B over Z. I know my 1/2 of my B would be 2 because I've divided my rectangle into 4 equally sized smaller rectangles, and Z is still 4. So my M value is 0.15. And then I would go to this handy dandy table that we used yesterday. So I would have a 1 and a 0.5, and I know my IC value is 0.15. 0.1202 from using this handy dandy table from yesterday. So I know my IC value is 0.12. My Q was given in my equation, in the problem. So I don't have to go through and calculate what P is and then divide it by A, because P divided by A is Q. So I can just use the Q value of 100 kPa that was given to me in the problem. So I know my Q value is, so delta sigma V is equal to Q times IC. So in this instance here, delta sigma V represents the increase in vertical stress associated with that load that was applied. So IC is equal to 0.12, Q is equal to 100, and then we multiply by 4 for the 4 rectangles. So we have 4 smaller rectangles that were represented by that, that were created from that one larger rectangle. So we calculated the increase in vertical stress to be 48 kPa. No, Pavel, we didn't officially have class yesterday. I just went through a few example problems. So my increase in vertical stress is 48 kPa. So my delta sigma V value is 48 kPa at the center. And I went through and did the same process at the corner, and my delta sigma V value at the corner of the foundation was 20 kPa. But we're just going to work through the center of the foundation. So I'm going to create the same table, or I recommend that we create the same table because I think it's easier to help determine if your material is initially, what its initial stress state is and what its final stress state is. So sigma V naught prime, which is your initial effective stress, is 54.6 kPa. So that's what we calculated it to be. What is your initial stress state? Is it normally consolidated or over consolidated? Right. So we know that our pre-consolidation pressure is 120 kPa, and we know our initial stress state is 54.6 kPa. So our material is initially over-consolidated. And so our increase in vertical stress due to the external load being applied is 48 kPa. So I know my delta sigma V is 48 kPa because I calculated it up here. So what's my final effective stress? What's my final effective stress value? How do I determine that? Right, 102.6. So 102.6 is our final effective stress state. So does this represent a normally consolidated or over consolidated stress state? Right. So our final stress state is also over consolidated. So what equation would we use if our initial stress state is over consolidated and our final stress state is over consolidated? Which equation do we use? Anyone know? Right, the over-consolidated equation. So here is the over-consolidated equation represented. Your CR value was given to you, and it was 0.08. H naught represents the total thickness of the clay layer, and the total thickness of this clay layer is 2 meters. E naught was given in the equation, and E naught represents the E value for the clay layer. It doesn't represent the E value for the sand layer, it represents the E value for the clay layer. So our E naught value is 0.824. We know our final effective stress is 102.6 kPa, and our initial effective stress was 54.6. So we calculated the amount of settlement that would occur at the center of the clay layer to be 24 millimeters, or 0.024 meters. If you wanted to go through what's the final one? The final one is OC because it's the final effective stress is less than your pre-consolidation pressure of 120 kPa. So our final effective stress is 102.6 kPa, and that's less than or smaller than our pre-consolidation pressure of 120. So that's why the final one is over-consolidated. The differential settlement represents the difference in settlement between the corner and the center of the footing. I didn't show the process here for how you would go through and calculate the settlement at the corner of the footing. It's the exact same process as what we did for settlement at the center. We've already calculated what our increase in external load, or what our increase in pressure would be associated with this, the load being applied at the corner. And you would just go through and create the same table and determine if your soil was initially over-consolidated, then what your delta sigma V value is, we already know, and you would go through and calculate your final effective stress. So again, it would represent an over-consolidated state initially and finally, but your amount of settlement would be slightly different. So when I went through and did the calculation, I calculated that you would have 12 millimeters of settlement at the corner of the foundation, whereas you would have 24 millimeters of settlement at the center of the foundation. So the differential settlement represents the difference in settlement between the center and the corner, and so that would be 12 millimeters. And it's just a coincidence that the settlement at the corner is equal to the differential settlement. So sorry, if we were to go through and then calculate what is the elastic settlement of the sand, to do this, we're just going to use the elastic settlement equation. We're going to use McCarthy's charts because we're assuming an infinitely thick sand layer. So we would just use this equation here. It's the same equation that we used this morning. We know what Q is, we know what B is, and we know what our elastic modulus is and our Poisson's ratio. The only value we need to determine is our factor, or our CS value. And we could simply just use McCarthy's chart. Gonna go and grab it. So if we know L over B is equal to 2 from McCarthy's chart, and we have a flexible foundation, so L over B of 2 for a flexible foundation would be 1.53 would be our CS value using the McCarthy's chart. That was from a previous one, sorry. So your CS value would be 1.53. So you could go through, CS is 1.53. You could go through and plug and chug through with the numbers. And again, it's just a complete coincidence that the amount of elastic settlement would be 12 meters, or 12 millimeters, sorry, in the sand layer. So if you wanted to know what the total settlement would be associated with this soil profile, you would add your elastic settlement from the sand layer and then your consolidation settlement from the clay layer. So your elastic settlement is 12 millimeters, your consolidation settlement is 24 millimeters, so your total settlement would be 36 millimeters. So I'm going to pause there and give you guys some time to copy and then review the question, and then I'm happy to answer any questions, and then we'll take a 10-minute break. Oh, I got lots of questions. Okay, I'm going to go to the top. Is the total settlement always at the center? Yes, we always take it at the center, typically, Tamiteo, unless they ask us otherwise, because the amount of settlement at the center is always the greatest compared to the corner. So we always take the worst case scenario. Yes, when the pressures apply when the pressure is applied, we assume it's constant and it's spread equally through the entire footing area. The sand settlement at the center or corner. Here we calculated the sand settlement at the center of the footing. And I would always calculate your settlement at the center because that is where you'll have the greatest amount of settlement. So it's our worst case scenario that we're designing for. Great questions, guys and gals. So this concept is something that you'll use probably quite regularly in industry. As you work more and more in the Red River Valley, this is something that you'll come across. And you may be asked to estimate the amount of settlement for certain project types. There are fairly stringent standards through the National Building Code and also through the Canadian Foundation Engineering Manual that we try to adhere to, especially for structures where there would be drywall or other types of material that could crack or break. Earth embankments are a little bit different. We can tolerate more settlement. Okay, I'll leave this up for those who want to copy. Otherwise, the rest of you can have a break, and why don't we meet back at 11:05, and then we'll go through settlement versus time. Are you guys okay with that? So yeah, come back at around 11:03, 11:05 in that range. Okay. Okay, I'm going to answer some questions. So hopefully those who put the questions in here are back. What is the Q in Q times IC? Q is stress or pressure in kPa. So that's what's represented by Q times IC. No, you would only calculate settlement for the corner and the center if I asked you to, but what I strongly recommend is that you calculate the settlement at the center. That's because that will always be the largest amount of settlement that the structure would experience. So always calculate the settlement at the center. Okay. The last question, where did the Q come from? That was in example problem 7.8. Q was provided in the example problem. It was given for the rectangular foundation. So that's where the Q value came from. No, so just calculate the settlement at the center of the clay layer and at the center of the sand layer. If I ask you for total settlement, that would be both your elastic settlement and your consolidation settlement in your clay layer. Otherwise, I might just ask you separately to calculate elastic settlement or consolidation. But in industry, you would add your elastic settlement and your consolidation settlement of the clay to get your total settlement. No, we're not going to use more circles for the stress. I took that out of the course. I didn't use it in 20 some odd years in industry. So you know what, it's great theory to know, but you're never going to use it in industry. So I removed it from the course. Okay, we're going to get moving on to time for consolidation now. This should be a little bit faster than the material that we have gone over. I'll lecture till about 11:30, 11:35. We should make it through most of the material. We might not make it through SPT and calculating settlement using SPT values, but I think that's a concept that you could easily follow on your own using the slides. So I'll post this presentation and then also following through with the example problems. But that is something that you will need to know for your test. Okay, time for consolidation. The rate of consolidation is defined by the rate at which the excess pore water pressure dissipates due to the water seeping out of the void space or seeping out of the soil layer. So last week we talked about how you would calculate your coefficient of your consolidation, which is your CV value. So that's the rate at which your the water seeping out or your excess pore water pressure is dissipating. The consolidation of the soil layer doesn't occur uniformly throughout. Your excess pore water pressure drains more quickly from the upper and lower regions of a soil layer than it does from a center. And remember, it also drains more quickly from the edges or the side than it does from the center as well. Percent consolidation. Percent consolidation is represented by the letter U. So U is the average consolidation of an entire soil layer expressed as a percent. So we can use this formula that we've provided, or I've provided on the slide. Delta H 100% is calculated using those formulas that we used in the last hour. So any of those three formulas for the normally consolidated, over-consolidated, or hybrid equation, the delta H value you calculate with that is your delta H 100%. The other delta H value is the percent consolidation that has occurred to date. So say, for example, I calculate my delta H 100 and I calculate it to be 100 mils. But I know at the present moment in time, I've measured the settlement or the amount of settlement that has occurred, and I know that only 65 mils of that consolidation settlement has occurred. Well, then I would say that my percent consolidation is 65% because it's the 65 mils divided by the 100 mils multiplied by 100%. So that's how I would calculate what percent consolidation has occurred or what is the average consolidation that has occurred to date. When we're looking at the design process, we like to ensure that we will consider our consolidation almost complete if we have 90% of the consolidation to have occurred. So if we want to calculate the amount of time that it's going to take for the consolidation to occur, this is the formula that's provided on this slide that we would use. I know I've probably harped on this a lot. So say we take, for example, that ring dike in St. Adolphe. We wanted to know how long it was going to take for us to get 90% consolidation. Well, when we did our calculations, it was going to take 256 years for us to get 90% consolidation to occur. So that's a really long period of time. Same with Brandon. It was going to be faster than that, but it was still going to be a significantly long period of time. For us to get 6 inches of settlement in St. Adolphe, that wasn't a problem. In Brandon, at 1.1 meters, that was a problem. So we had to use wick drains to accelerate the settlement so that we could construct the approach embankment for the bridge there. So this is the equation we use to determine how long it is going to take to reach a certain percentage of consolidation to occur. So in this equation here, T is represented by time. Because our CV value is measured in millimeters squared per minute, the time is generally represented by minutes. D represents your longest drainage distance, and the longest drainage distance depends on your soil stratigraphy. So I'll have a discussion in a few slides on how you calculate what your longest drainage distance is. And TV is a time factor, and this time factor depends on your U value or your percent consolidation. So you can use a graph or a chart to determine what your TV value is. This is the graph or the chart that you can use to determine your TV value. Either or is fine on a test. I try to give values on a test such as so that they're whole percentages, like somewhere between like 10, 20, so like a 10 value or a 40 value or a 90 value. So it's fairly easy to determine what the TV value is. Otherwise, if it doesn't lie or if it's not shown on the table here, you can use the graph to determine what your TV value is. Your longest drainage distance, there's two possibilities for your longest drainage distance. The first possibility is, say you have a clay layer, and that clay layer is bound above and below by two permeable layers. So you would have a sand layer that's above the clay layer and a sand layer that's below the clay layer. Well, your longest drainage distance for that clay layer is actually represented by 1/2 of your clay layer thickness, or your H/2 value. That's because if you were to look at a molecule of water that's at the center of your clay layer, that molecule of water can either drain in the upwards or downwards direction. So if it can drain in either direction, the longest distance that molecule of water will ever travel is 1/2 of the thickness of that clay layer. So if your clay layer is drained from the top and the bottom, your drainage distance D is represented by your H/2 value. That being said, if you have a clay layer that is bound on the top or the bottom by an impermeable layer, so it might have a sand layer above and an impermeable layer below, or an impermeable layer above and a sand layer below, but that same molecule of water can only drain in one direction, and it will drain towards the permeable layer. So if we look at this example here, we have a molecule of water that's at the base of the clay layer. Well, it's not going to drain down into this impermeable layer. It's going to drain in an upwards direction towards this sand layer. And so in a scenario such as this, the longest travel distance, or the longest travel path for that molecule of water, is the actual thickness of that clay layer. So D is represented by H, which is the total thickness of your clay layer. I'm going to pause here and see if anyone has any questions. I guess you guys didn't see me speaking. Sorry about that. Any questions about the information that I just presented?
If you're building right on top of a clay layer, would your let's say you had like a foundation that was completely covering the clay layer, would that be considered an impermeable layer?
Yes, if the soil above it was also clay, yes.
Okay.
If you had, say, a clay layer that was open to the atmosphere, so like just open, you know, to the air, then it would only be considered bound on one side. So it would depend on what the stratigraphy beneath the clay layer is as well. So likely in the Red River Valley, the stratigraphy beneath the clay is a silt or a sandy type of till. So that's where it would drain to, either there or to the atmosphere, like to the ground surface. But if you had a clay layer above it, it's considered impermeable above, the foundation area. It's going to want to drain to the sides. So sometimes there's sand or silt seams within the clay, and that's where the water is going to want to drain to, if it can. Good question. Anyone else have any questions? Okay, no? Okay, I'm going to go through a few example problems. I'm going to go through example problems 11, 11, and 11, 14, or you might see them on the notes as 7, 11, and 7, 14. So I went through with example problem 710, and I calculated what our delta H 100% was going to be. So our delta H 100% is 62 mils. So when we're using that 62 mils in this next problem, that's where the value came from. So if we look at example problem 711, it's asking you to calculate the time that it takes to reach 90% consolidation for a 3-meter thick soil layer in example problem 710. So the example problem in 710, I believe it had a sand layer above it and a sand layer beneath it. So the clay layer wasn't bound by anything impermeable. It had a permeable layer above it and a permeable layer below it. So that information was presented. So it had permeable sand layers above and below, with the consolidation coefficient for the clay being 3.55 millimeters squared per minute. And that would have been calculated from a consolidation test. And then it says, note, there are 1,440 minutes in one day. So what information can you garner from this question? Well, you know you want to calculate the amount of time that it takes for 90% consolidation to occur. So if we look at the first parameter of the equation, it's our D value. So D can be represented in two ways. What do you guys believe the D value would be in this situation if the clay layer has sand above and below it? Correct. It would be your H over 2. Correct, because that molecule of water can drain in either direction. It can drain upwards or it can drain downwards. So our D value is H over 2. One thing I caution you with, and you have to do for these questions, is you have to convert the thickness of your clay layer to millimeters. So I think it says 3,000 meters there, but sorry, it's supposed to be millimeters. That's because your CV value is in millimeters. So you have to have consistent units throughout the equation. So convert the thickness of your soil layer to millimeters. So in this instance here, the thickness of our soil layer is 3,000 millimeters, or 3 meters. And we're going to divide that by 2 because the clay layer has a permeable layer above it and below it. So our D value in this question would be 1,500 millimeters. So we know D. TV, we would have to determine TV. And we know CV because CV was given in the equation, and it's 3.55 millimeters squared per minute. So we know that we want to calculate the time it takes to reach 90% consolidation. So if we go to this handy dandy chart or equation, or sorry, a chart or graph, I know I want to calculate the amount of time it takes to reach 90% consolidation. So if my U value is 90%, I know that my time factor, my TV value, is 0.848. So I don't have to use the graph because I have this table here, which makes it easy for me. So my TV value is 0.848, and then I divide that by my CV value. So I would calculate, I calculated 373 days, but if you were to calculate in minutes, you would calculate it initially in minutes. You would get 537,465 minutes. And I just converted that to days by dividing by 1,440 minutes in a day. And I was able to determine it was going to take 373 days for this 90% consolidation to occur. Anyone have any questions? Sorry, Sean.
When
Yes.
you say 373 days, does winter affect that?
It does in the sense of freeze thaw, but once you get below the frost depth, it doesn't impact it. But it would a little bit, Sean. You are correct. Not astronomically, because there's only the upper 10 feet, right, or 9 feet that would be impacted by freeze thaw.
Okay.
But it will a bit. Yes, it will. Okay, well, let's go over example problem 714. It's a similar type of example problem. So it's saying for the same soil layer, calculate the amount of consolidation after 6 months. So here is the problem has indicated to us that there's 262,800 minutes in 6 months. So we know that delta H 100% is 62 mils. So what I like to do is I like to write out the equation and figure out what my unknowns are. So I know our equation T is equal to D squared times TV over CV. I know what my D value is because it's the same soil layer. So it's drained above and below. So I know my D value is equal to H over 2. So I know my D value is equal to 1,500 millimeters. I know my CV value is 3.55 millimeters squared per minute because it's the same soil. And I know the time is 262,800 minutes. So the only unknown I have in this problem is my TV value. So I will go through and I'll solve for my TV value. And if I plug and chug through, I know that my TV value is equal to 0.415. So then I'm going to go to my handy dandy chart here. And I know from this TV value, I'm able to determine what is the percent consolidation that has occurred. So I calculated my TV to be 0.415. And obviously that falls somewhere between the 70 and 80% range from just looking at the table that's provided. So I used the graph here and I tried to graph as best as I could where 0.415, my TV factor, would intersect the curve. So I drew my line from about this point. I drew a vertical line up to where it intersects the graph, or this line on the graph. Where my TV value intersects the line on the graph, I drew a horizontal line over to my y-axis, and I was able to determine that I had approximately 72% consolidation that's occurred over that time period of 6 months. You might say it's 71, someone else might say it's 73, but that's not a problem. So if I know that that 72% of the consolidation has occurred, I can calculate how much settlement has occurred to date. So I know that my U value is equal to my delta H value divided by delta H 100%. So I know delta H 100% is 62 mils, and I know my U value is 0.72. So I can calculate that my delta H value is about 44.6 millimeters. So I know that is about 45 mils of settlement has occurred over that 6-month time period. I'm going to pause there and give you guys some time to review this. Does anyone have any questions? No, the way I'm doing it is I'll just give you what delta H 100% is in the to do the calculations. So it won't always be 62 mils that would be provided. This was just the number that was provided in this question. It would be a different value, but I'll provide delta H 100% or make it very, very clear how you would determine what that value is. Okay, what do you guys feel like? Do you want me to work through SPTs and how you would calculate elastic settlement using SPTs? Or we've gone through a lot today and really you wouldn't be able to take it in? Well, you guys would go through it on your own. I could make videos of working through the solutions, but it would just be theory material that you would review on your own and do the calculations. I don't mind having like an open question and answer period next Wednesday or Thursday, whatever works better for you guys before the test. Just let me know. Do you guys want some time to digest what we presented today? And then Wednesday or Thursday of next week, do you guys want an open question and answer period where you can come in and out of my personal room? Oh, you have too many tests next week. I thought you had all your tests this week.
We have 3 next week.
Again? Oh my goodness. That's
2
not good.
midterms and your test.
Okay, what class do you have midterms in? I guess economics?
Economics and payment.
I just said you just had a payment test, didn't you?
No, that's just one of his 2-hour quizzes.
Oh goodness. Okay. Well, what works? Yeah, it never ends. I can see this. What works best for you guys? Like
Maybe a question period like after Wednesday, kind of before the test.
Okay. I'll do videos. And then I will also have an open-ended question period. Would you guys prefer Wednesday afternoon or Thursday morning? Thursday morning? I don't know what you guys have in supervisory management. Well, why don't I do 1 hour on Wednesday and 1 hour on Thursday? So those who want to ask questions on Wednesday can ask them on Wednesday, and those who want to ask them on Thursday can ask them on Thursday. Does that work?
Yes, thank you very much.
Okay, no problem. So I will send one of my very detailed emails about the test again. I will completely lay out the test with how many questions there will be in each section, how much each question will be worth, and I will send graph paper, both regular graph paper and semi-log graph paper, and there's only one question that you will need to hand in work for. You will still have to read over field instrumentation on your own as well, but if you have questions on it, you can ask me next Wednesday and Thursday. So I'll have one discussion or open-ended question period on Wednesday afternoon, and I'll have another one on Thursday morning. So hopefully you guys found today informative. Again, I'm open to like suggestions on how I can better assist with the learning process.
I don't know if I missed it, but did you say when you were going to post the quiz?
Right after class.
Okay.
I have them all marked. So I'll just upload the marks, and then people can look where they potentially made some mistakes on the quiz. But I'm gonna, at the end of this class, I will go and open them up, and then everyone will have access to it. I guess if anyone has any questions, they can stay on the line. Otherwise, I'll send you an email, a detailed email on the test, and then I'll send you an email giving the times on Wednesday and Thursday for the question and answer period that people choose to attend. I won't formally have anything prepared, but I will be available to answer questions that students have. And in the meantime, you can always just send me an email or ask to meet with me privately before then. I will be available. I thank you guys for coming today very much, and I know it's been a long week, and it sounds like next week will be a long week. I wish my course wasn't on Friday. I wish you could have had something else on Friday, but I guess that's the way the cookie crumbled. So have a great day, and I will go and open up your quizzes for you.